Welcome to The Explainer. Today, we're going to pull back the curtain on your computer. We're breaking down the fundamental pieces that make it all work, from the moment you type a command to the magic that happens inside.
So let's just dive right in. You've written some code, you hit run, and poof, something happens. But what is that poof exactly? What's the real journey your instructions take? Well, we're going to follow that path step by step.
You know, everything, and I really mean everything, begins its journey in what you can think of as the computer's giant permanent library. We're talking about the disk, or what you probably just call your hard drive.
Now, the key word to remember here is persistently. This is your computer's long-term memory. Doesn't matter if it's an old-school spinning hard disk drive or a new fancy solid-state drive. Its job is to hold on to your files, your OS, your games, forever, even when you turn the computer off. And the biggest advantage of the disk? Its sheer size. It's massive. We're talking terabytes these days, which is a trillion bytes of information, a huge digital warehouse. But, and this is a big but, getting information out of this warehouse, it's actually pretty slow in computer terms.
Okay, so since that main library, the disk, is kind of slow, the computer needs a much faster place to do its active work. So imagine setting up a workbench right next to the library for easy access. Well, that workbench is your RAM. RAM is your computer's ultra-fast but temporary workspace. When you open an app, it's pulled from that slow disk and loaded into lightning-fast RAM so you can work on it right now. The catch? RAM is what we call volatile. The second you turn off the power, poof, everything on that workbench is just gone. It remembers nothing.
And this right here, this is the fundamental trade-off. On one hand, you've got the disk. It's huge, it's permanent, but it's slow. On the other hand, you have RAM. It's incredibly fast. We're talking maybe 1,000 times faster, but it's way smaller and totally temporary.
So, who's the actual worker in this whole setup? You know, the one running back and forth between the library and the workbench, doing all the work? Well, let's meet the brains of the operation, the central processing unit, or the CPU. The CPU is the engine that makes everything go. It's the part of the computer that's doing the actual thinking. It can't really store much data itself, but its job is to fetch your instructions, move data around, and do all the math. It's the one in charge.
And really, the CPU's entire existence just boils down to this one simple loop that it does over and over and over again. Fetch an instruction from memory, read or write the data it needs for that instruction, and then compute the result. And it does this billions of times, every single second. It's insane.
But here's where it gets really interesting. CPUs have become so ridiculously fast that now even waiting for RAM, which we just said was super fast, is too slow. The CPU is sitting around tapping its fingers waiting for data. It's become a bottleneck, so it needs an even faster shortcut.
And that's where the cache comes in. The best way to think about this is like the CPU's own personal tool belt. It's a tiny but absurdly fast little pocket of memory built right onto the CPU chip itself. And its only job is to hold the data and instructions the CPU uses most often so it can grab them instantly.
Now, to make sure it's working as fast as humanly, or I guess siliconly, possible, the CPU doesn't just look for data randomly. It has a very specific, very smart strategy.
So whenever the CPU needs a piece of information, the very first place it looks is its tool belt, the cache. If the data is right there, awesome. That's called a cache hit, and it's basically instant. If it's not there, a cache miss. Then, okay, the CPU has to take that slightly longer trip to the workbench, to RAM. But here's the clever part. It grabs the data, and then it puts a copy of it in the cache, just in case it needs it again soon.
And all these pieces together create what we call the memory hierarchy. It's a pyramid of trade-offs. At the very bottom, you've got the slow, but massive and permanent disk. A step up, you have the much faster, but smaller and temporary RAM. And right at the very top, you have the tiny, but unbelievably fast cache. And I need you to understand, the speed difference here is staggering. It's not just a little bit faster. Let's put this in human terms, right? If getting data from the cache is like grabbing a tool from your pocket, then getting it from RAM is like having to walk all the way across the room to your workbench. And getting it from the disk, that's like getting in your car and driving to a warehouse across town. That's the mind-blowing difference between nanoseconds, microseconds, and milliseconds.
This whole system, this hierarchy, it's brilliant. It's served us incredibly well for decades. But for all its cleverness, we are starting to slam right into a fundamental wall. And that wall is the laws of physics.
For decades, the entire world of computing was driven by this one simple observation, which you've probably heard of, Moore's Law. It basically promised us that our computers would get twice as powerful, twice as fast, about every 2 years. It was an amazing ride.
And for the longest time, it worked. All through the 90s and 2000s, computers just kept getting exponentially better. But look at this timeline. In the last decade or so, that incredible curve has started to flatten out. We're hitting a plateau. We're just physically running out of room to shrink transistors any smaller.
And here's the big takeaway from all this. It means that the era of just waiting a couple of years for a much faster computer to come along and solve our biggest problems, well, that era is kind of over. The speed of a single machine just isn't growing like it used to.
So that forces us to ask a really important question. If we can't just keep making a single computer faster and faster to solve the massive challenges of today, what do we do? What's the alternative? How do we keep pushing forward? And that, well, that's a question we'll have to tackle next time.
Welcome to The Explainer. Today,